And now let us give you some example of computation of derivatives. So, examples of computation of derivatives. Okay, first example. F is defined on the whole real line, which is an interval, and f of x is constant. So let x bar, the point where we want to compute the derivative, be a real number. Then we have that f of x minus f of x bar. We want to compute the increment, and this of course will be c minus c, which is 0. But we can write 0 in a sort of funny way, quite baroque way, but this is what we want to do, like 0 times the increment in the x. What remains is 0, so we can again write here 0 times x minus x bar plus little of x bar for x going to x bar. Of course, this is a sort of stupid way of thinking, but just to give you the first elementary example, here we have 0. 0 is little of everything. Okay, so, but we want to get at the end an expression like this, where there is a part which is proportional to the increment in the independent variable and a little o. So here we have 0 written as 0 times the increment in the x, and here we add an infinitesimal of higher order. Of course, this is another 0, so it is of higher order of everything you can think of. However, this is the writing we wanted. So the conclusion is that since we get this expression, we conclude, applying the definition of differentiability and of derivative, that f is differentiable at x bar whatever is our choice of x bar, and f prime of x bar is equal to 0. Okay? So, second, again, f is defined on the whole real line, and f of x is equal to x to the mth power, where m is a natural number, and so we have to differentiate the power, and again we consider x bar as a point, an arbitrary point of the real line. Again, we write down the increment, which is f of x minus f of x bar, and this is x to the nth power minus x bar to the nth power, and this is, by the usual decomposition we know very well, this is x minus x bar, and here x to the power m minus 1 plus x m minus 2 x bar plus, and here many dots, plus x bar to the power m minus 1. Okay? Now, let us observe the following stupid statement: x to some power j is equal to x bar to the same power j, plus an infinitesimal, so to say little of 1 when x goes to x bar. Now you should be used to this sort of writing, but if it still sounds exotic to you, just consider that this means that the limit for x going to x bar of x to the jth power is equal to x bar to the jth power. Then again, going back here, we have that f of x minus f of x bar is equal to x minus x bar. And here we write simply x m minus 1 as x bar, m minus 1 plus little o of 1. And here we have, and this is a, let me, just to identify what is the term we are considering here. And here plus, this time x minus 2 x bar. So we have x bar to the power m minus 2 plus little o 1. Everything multiplies x bar, and this is the yellow term, and so on and so on. So it is clear how we proceed, and plus many dots plus x bar to the power n minus 1. So let me proceed very, very slowly. And so x bar m minus 1 plus little o of 1. And here we just notice that x bar times little o 1 is equal to little o 1. So here plus x bar again m minus 1, because here we have to multiply these two and we get x bar to the power m minus 1 plus little o 1. And so for the other terms it is the same up to the last term, which is directly x bar to the power n minus 1. So we have x minus x bar, and here inside this bracket we have n times x bar to the power m minus 1. So it is m times plus little o of 1. Now we extract from the bracket every term, and so we have m x bar to the power m minus 1 that multiplies x minus x bar plus little o of x minus x bar for x going to x bar. Okay? And so this is exactly the statement we looked at in order to get the definition of differentiability and of derivative. So we have here that f is differentiable at x bar, and f prime of x bar is equal to m x bar to the power m minus 1. Okay? So this is the second elementary derivative I wanted to compute. And the third here is again a function defined on the whole real line f from R to R, and f of x is equal to sine of x. And x bar is a real function, and we have that f of x minus f of x bar is equal to sine of x minus sine of x bar. the famous formulas, prostaphäresis on the difference of signs, says that this difference is equal to 2 times sine x minus x bar divided by 2 cosine x plus x bar divided by 2. We know already from previous limits that we studied in detail that this is equal to x minus x bar over 2 plus Lied law of x minus x bar, while this cosine, the cosine is a continuous function, so this is cosine of x bar plus Lied law of 1. So developing everything, we find that this is 2 x minus x bar over 2 plus Lied law x minus x bar times cosine of x bar plus Lied law of 1. Of course, this 2 factor goes away and it doesn't touch the Lied law, and so we have cosine of x bar that multiplies x minus x bar plus, and here we have to multiply everything here times O x minus x bar, and this is again Lied law x minus x bar. So this is plus Lied law x minus x bar as x goes to x bar. So as a conclusion, again, f, so sine of x is differentiable at the point x bar in R, whatever is x bar, and f prime of x bar is equal to cosine of x bar. And another way of representing this is a more formal, so there is some abuse of notation here. We can say that sine of x prime is equal to cosine of x. And then here the fourth example is, of course, the cosine. Again, f from R to R. F of x is equal to the cosine of x, and let x bar be any real number. And so the increment of the function f is the following: f of x minus f of x bar is equal to the cosine of x minus cosine of x bar. And again, the same prostaphäresis formulas tell us that this is equal to minus 2 sine of x minus x bar divided by 2, and then sine x plus x bar divided by 2. This is equal to, again, minus, as before, we end up with x minus x bar plus Lied law of x minus x bar. And here we have sine of x bar plus Lied law of 1 as x goes to x bar. And this is equal to, the factor this time is minus sine of x bar times x minus x bar plus Lied law of x minus x bar. And the fifth, so again we can say that f is differentiable at x bar, every x bar in R, every x bar in R, and f prime of x bar is minus sine of x bar. So the derivative of the cosine is minus sine. Remember this, don't fall into very naive mistakes on that. So the derivative of the sine is the cosine, and the derivative of the cosine is minus sine. So cosine of x prime is equal to minus sine of x. Okay? This is very easily seen. And so last example, extremely important, are in R. So f of x is equal to e to the x, and again let x bar be a real number, and so f of x minus f of x bar is equal to e to the x minus e to the x bar. So here let's gather e to the x bar, and here you end up with e to the x minus x bar minus 1. And from usual limits that we know, this is equal to e to the x bar, and this is x minus x bar plus little o of x minus x bar, as x goes to x bar, and this is equal to e to the x bar x minus x bar plus little o of x minus x bar when x goes to x bar. And again, f is differentiable at x bar in R, regardless of what really this x bar is, and f prime of x bar is equal to e to the power x bar, so to say that e to the x prime is equal to e to the x. And this is a very important property, very far-reaching property, is the following. Is that e to the x is left untouched by the differentiation, by the derivative. Oh. And now the question can be, what about non-differentiability point? So some points of non-differentiability. The first thing to be said here is the following theorem. Or it is not so huge as a theorem, let me say just proposition. If a function f is differentiable at x bar, then f is continuous at x bar. So proof. So as a forward, if f is differentiable at x bar, then by definition of differentiability, x bar must be an internal point of the domain of f. Therefore, in order to show differential continuity, we just show that the limit of f when x goes to x bar is equal to f of x bar. So it is equivalent to f of x is equal to f of x bar plus Lie the law of 1 as x goes to x bar. So again, differentiability says the following, that f of x is equal to f of x bar plus f prime of x bar, x minus x bar plus Lie the law of x minus x bar as x goes to x bar. But of course, if it is Lie the law of x minus x bar is infinitesimal, so this is also Lie the law of 1, and this is Lie the law of 1 too. Why? Because there is the factor x minus x bar here. So immediately we have that this is equal to f of x bar plus Lie the law of 1 as x tends to x bar. Then f is continuous at the point x bar. So now that very natural question is whether the converse is true. So it is true that if f is continuous, then f is differentiable. Please be careful here, because I always find a lot of mistakes in the written exams about that. So, very important remark. The converse is not true. The converse is not true. It means that f continuous at x bar does not imply that f is differentiable at x bar. Why? In order to deny an implication, we just have to give one specific counterexample. The typical counterexample one does is the following. Consider f from R to R. F of x is the absolute value of x, and x bar is 0. Okay, and this is the graph, which is well known, and we will draw it still several times. We already had to draw it several times. And notice that at 0, the situation is that you really have a corner point here. And the corner point means that there is no tangent here. You may argue that there are two tangents, but this is not true, because if you come here from the right, the tangent you can suggest is this one. And this is good tangent at right, but it is not tangent at the left. So x less than 0. Oh, sorry, let me say at left. And vice versa, if you come from the left, you may guess that the tangent here is this. But this is not tangent at right. And this is tangent at left. This is just an intuition, because you say that here that here the distance between this suggested tangent and the true curve is not Lie law 1. It is not a smooth, okay? But of course, sorry, it is not the Lie law of x minus x bar. It's only Lie law 1. But of course, it can be misleading, it can be deceptive to try to guess such a behavior just by a picture. Just keep the intuition and translate it into computation. Indeed, you have f of x if you have f of x minus f of x bar, this is equal to modulus of x minus 0, and this is x. This is, sorry, modulus of x, and this is x for x larger than 0, and minus x for x smaller than 0. And this is equal to what? To x plus 0, which can be described as x plus Lie law of x for x larger than 0, and here, let me write it, minus 1 times x plus Lie law of x, and here will be 1. X less or equal to 0. So, therefore, f is not differentiable at 0, since there is no, it is not necessary to tell this, but I want to stress it, there is no unique number m such that modulus of x minus 0 is equal to m x plus Lie law of x as x tends to 0. There is no unique that. There are two, one which holds for positive x, minus one which holds for negative x, and this is the reason why here there are two tangents. One tangent with angular coefficient 1 that is good for positive numbers, and another candidate tangent with angular coefficient minus 1 for the negative part of the domain, but there are no two tangents. The tangent is one line, and it has to be unique. And so here there is no tangent, there is no derivative. And another method in general, more popular, you probably already know that, another method to compute totally equivalent, just a matter of language, to compute derivatives is the so-called limit of incremental ratio. Incremental ratio is nothing but the coefficient of the lines, of the second lines. So the quantity f of x minus f of x bar divided by x minus x bar is called the incremental ratio. And differentiability states that f of x minus f of x bar is equal to f prime of x bar times x minus x bar plus Lie the law of x minus x bar as x goes to x bar. And this is true if and only if the limit for x going to x bar of f of x minus f of x bar divided by x minus x bar is equal to f prime of x bar. Okay? So the derivative is the limit of the incremental ratio. So you can recompute all the derivatives I computed before by doing this, in this language of the limit of incremental ratio. It is completely equivalent. Use what you prefer. I know that you now prefer the limit of incremental ratio simply because it is the method that you already know. But I ask you also to use the other method, learn it, and then choose what you want. Okay, it is important. The derivative is the limit of incremental ratio. Okay, now use it for this example of the absolute value. In this example, we have that the limit for x going to 0 of modulus of x minus modulus of 0, which is 0, divided by x minus 0, is equal to the limit for x going to 0 of modulus of x divided by x. Here we have that the right limit is 1, and the left limit is minus 1. So since the right and the left limit differ from each other, so we have that the limit of the incremental ratio does not exist. So the derivative at 0 does not exist. And so the tangent to the graph at 0 does not exist. So we are very happy. Everything is coherent in this framework. And so basically this is the end, and an important remark is the following: the same happens for all corner points. When you have a corner points, for instance, a function like this, and then it starts again like this. This is a non-differentiability point. Okay? So, and non-differentiability points are points of the domain of the function. So when at the written exam we always do that, we ask you the non-differentiability point, don't tell me the points that are outside the domain. This is a mistake. Okay? Points of the domain in which there is no derivatives. Okay? So, so they are, first, non-continuity points. Second, corner points. And third, cusps. Cusps are points in which the limit for x going to x bar from the right of f of x minus f of x bar divided x minus x bar is plus infinity or minus infinity. Or the limit x going to x bar from the left of f of x minus f of x bar divided x minus x bar is plus infinity or minus infinity. These are very spiky corners. What does this very spiky corner means? So if I can give you some examples. Okay, I will, now I don't have in mind any example, I will have some example, and it means that they are like something like that. This is a corner, and this is a cusp. So the tangent here tends to be vertical, this is the idea, at least from one side. Sorry. So this is a cusp, vertical tangent. So here in general, so points outside the domain are not to be considered as non-differentiability point. Okay? They are just outside the domain, and exactly as they are not to be considered as non-continuity point. Typical example that now you can expect is the following. F of x, f defined in r minus 0 to r, f of x is equal to 1 over x, and here is the point. Okay, this is not a non-differentiability point. 0 is not a non-differentiability point. As it is nor a point of non-continuity. It is simply a point which is outside the domain. Okay? And here, just stop.